All right, in the statically indeterminate item here, we've got a rigid bar, ACEB right here. This whole long bar is considered rigid. It would be in bending, but we're going to consider it that it doesn't actually have any bending deformations. And of course, at this point in the course, we wouldn't know how to deal with it anyways. So we'll consider that as rigid. The flexible pieces are these rods, CD and EF. Right? And we have a 2,000 pound force that's applied up here at the mid-height of this thing. The system is pinned down here at A to the rest of the world. It's pinned at D and it's pinned at F. These are locations that there are no translations. There are rotations potentially because there's a pin there. There's nothing from the external part of the world to prevent that. Right? So note, no applied loads to member CD and EF, only they are just pin connected members. So as this force of 2 kips is trying to do something, displace the system, there's a external pin at A, flexible things going on at CD and EF, so this thing wants to try to rotate in a clockwise kind of fashion. Right? No translations at A. Flexible things going on here at the 2 links. So no direct applied force to CD from an external standpoint, but internal effects. These 2 rods keep this bar from freely rotating. They keep it stable, so to speak. Right? It's statically indeterminate, as we'll demonstrate in just a moment. We're supposed to draw the complete free body diagram and then come up with the related single equation of equilibrium that we would eventually use to find the forces in those 2 rods. And so how we do that, of course, here's our free body diagram. We must have the reactions here to have a complete free body diagram. Doesn't matter that we're clever and we're going to sum moments about point A to get our appropriate equation. Some of you said, I'm going to sum forces in the X or sum forces in the Y. That ain't going to help you a whole heck of a lot. And if you miss off AX and AY, then those equations are completely invalid. You got to have it complete. Right? So who cares what the values are? Ultimately, because I can write an equation that only involves these 2 unknowns by summing moments about point A. And so the force at E, force at C, if they're moment arms, there's the moment arm associated with applied force, and we get a nice simple little equation. Now you see I kind of crossed out the E and the C and put NE/NC because I realized after the fact that, gee, capital E is also our elastic modulus, and that's going to show up somewhere else. So that was a poor choice initially of the symbols for the forces. But here's our answer for that basic equilibrium equation. Notice, 1 equation, 2 unknowns. We only have, out of the global free body diagram, 3 independent equations of equilibrium. But we got 1, 2, 3, 4 total number of unknown forces. That's why it's statically indeterminate to the 1st degree, because we have 1 more in excess of the equations of equilibrium. So we can't just write any old bizarre set of equations. We've got to have a complete free body diagram to go with our equations, and if you do it this way, you get the nice simple deal to work with. Right? The displaced shape that we're going to work with then to get the compatibility equation that will make all this work is, again, to recognize the bar itself is rigid, and it will then rotate about the truly external point that does not translate here. So you go to the pin at A. This is just like the examples, right? I mean, it is exact. Oh, well, hey, you put the bar vertical instead of horizontal. Well, who cares? Right? What difference does that make? Well, gravity. But gravity's not included in the problem. So go with what we actually have in the model. Right? That's part of the key. All right, so it's just like the examples. And so there's our distances: 1 foot from the pivot to C, 3 foot from the pivot to E. That sets up our similar triangles. The displacement at E will be 3 times the displacement at C. But won't that bar bend? Yes, it will. But guess what? Remember, we're going to call it rigid. So that's more complex. We don't know how to deal with that anyways. This is the way to go about doing this. Delta E equals 3 times delta C. Now we can look ahead and say, hey, the displacement at E is going to be equal to the axial shortening or elongation of the rod EF. Likewise at C, that's going to have the rod CD. It's all directly in line. Delta E and delta C are horizontal displacements, and the two rods are exactly horizontal, so that relationship is exactly equal to 1. If those rods were inclined, then the x displacements at E and C would not be exactly equal. They'd be some sort of portion of it. Right? And then we need that force deformation relationship to finally begin to solve for the unknowns. All I was asking for here is, hey, this thing going on right there, right, that is an axial deformation. There's our model. Substitute in. Note we got a lot of commonalities here. Same cross-sectional area, same material. The lengths are different. So that's the key. That's what I'm looking for on the test. You could take it a step further, substitute in for into the compatibility equation, and get ultimately, after you cancel out a few things, a nice simple looking expression here. NE equals 6 times NC. That comes back up into here. Now we have an equation that has only one unknown. We can solve for them, and away we go. But that was not required nor expected. Right? You're not required to find the value of the forces in the rod, just to find those three specific things.